Welcome to this explainer. Today, we're diving into the absolute massive scale and, honestly, the fascinating physical engineering behind drilling mud components. If you've ever looked at a rig and wondered about those towering silver silos flanked by hoses, you are looking at the beating heart of the mud system. We're going to break down exactly how these bulk systems work, why they are absolute lifesavers during an emergency, and the invisible, permanent hazards they hide. Here is our roadmap for today. We'll hit built by the ton, bentonite and barite, flowing like a liquid, waiting up a kick, the barite formula, and finally, the invisible dust hazard. Let's get right into it.
Section 1. Built by the ton. Mud ingredients.
To really wrap our heads around this system, we've got to completely shift our perspective on what drilling mud actually is. You see, it's not some pre-made liquid you just buy in a barrel. It's a highly engineered, totally custom recipe, water mixed with an enormous amount of dry powder, and you have to build it on site continuously the whole time you're drilling. And guys, the scale here is just staggering. A single well literally drinks hundreds of tons of dry powder. You absolutely cannot run an operation of that magnitude by ripping open paper sacks by hand. There's just no way. That's exactly why, beside every rig, you're going to see these tall steel storage tanks, usually hopper-shaped, just standing by, ready to deliver powder into the system on demand. Section 2. Bentonite and barite, primary ingredients. So let's peek inside those massive silos at the two main raw ingredients that make up the bulk of our mud additives. First up, we've got bentonite. This is a clay, and its one and only job is to provide viscosity. It gives the mud that crucial thickness needed to physically carry crushed rock cuttings all the way from the drill bit right up to the surface. Then we have barite. Now, barite is a remarkably dense mineral, and it is strictly there to give the mud its heavy weight, which is what holds back the formation pressure. So you've got two completely different materials, both stored in just massive quantities. Moving on to Section 3, flowing like a liquid, pneumatic transfer.
Now, this brings us to a pretty massive engineering challenge. How in the world do we move hundreds of tons of these dense minerals into the mud without a single person lifting a shovel? Well, the magic word here is pneumatics. By injecting pressurized air right at the base of the silo, the dry powder actually fluidizes. The air gets in there, separates the microscopic particles, and suddenly, it's like magic. The whole solid mass flows and pours exactly like water. It gets blown down a hose straight to the mixing hopper, where it meets a water jet and is sucked right into the mud stream.
If you're having a hard time visualizing this, just picture a bulk cement truck blowing powder onto a construction site. Or think of a massive flour silo at an industrial bakery. The rig uses that exact same pneumatic transfer physics. Dry powder, pressurized air, and fluid-like flow. It's the exact same tech.
All right, let's pause for a second and test your understanding with a real-world scenario. Imagine you urgently, and I mean urgently, need to move powder to weight up your mud. But suddenly, the flow chokes and just stops. The hopper absolutely won't take the barite. So what do you think is the most likely cause of this failure?
The culprit? Moisture. If the air supply isn't perfectly dry or if the silo isn't totally sealed, that damp powder clumps together. It cakes up and forms a solid bridge right across the bottom cone of the silo. When that happens, the pressurized air just blows straight through a hollow channel in the middle instead of fluidizing the whole mass. And let me tell you, absolutely nobody wants to discover their barite is caked solid on the exact day they actually need it. Section 4. Waiting up a kick. Well control. Let's see how this whole system plays out in an actual, real-life emergency. When a well kicks, which means dangerous formation fluids start forcing their way into the wellbore under high pressure, the only cure is heavier mud. And heavier mud means you need barite, fast, and in extremely large volumes. Running low on barite isn't just a minor logistical inconvenience, guys. It represents a total loss of your ability to kill the well. Your bulk barite silo is quite literally your primary well control tool. Period.
Section 5. The barite formula. Calculating the load.
Because barite is absolutely critical for well control, we can't just guess how much to dump in, right? We use the standard mud engineer's equation. To figure out how many sacks of barite you need per 100 barrels, you take 1470, multiply that by the desired weight minus the current weight, and divide the whole thing by 35 minus the desired weight. So if we need to take a system from 12 to 12.5 pounds per gallon, the math says we need about 33 sacks per 100 barrels. Now, on a standard 1,000-barrel system, that comes out to 330 sacks. You are definitely not carrying that by hand. It proves exactly why pneumatic bulk transfer isn't just nice to have, it's absolutely mandatory.
And finally, Section 6, the invisible dust hazard, silica exposure.
So we've seen how incredibly powerful this system is, but we urgently need to talk about the hazards. Bulk powder systems share two major dangers. First, pressure vessel ruptures, because let's face it, those silos are essentially giant steel balloons full of pressurized air. And second, dust. Both barite and bentonite contain respirable crystalline silica. OSHA strictly limits exposure to just 50 micrograms per cubic meter over an 8-hour shift. To put that into perspective, that is a microscopically small amount of dust. Breathing in this ultra-fine silica dust causes a condition known as silicosis. And listen, it's not just a bad cough. It is a permanent, completely untreatable destruction of your lung tissue. But what makes it so incredibly insidious and dangerous is the timeline. It takes years to actually materialize. Since the initial damage is completely invisible, the workers who eventually get silicosis, they never felt a single thing wrong on the day they were exposed. They literally just breathed in a little white dust over by the hopper. So I'm going to leave you with this final provocative thought. Will you be the one to ensure the respirator is worn every single time? Because at the end of the day, it is the only thing standing between a routine job and a devastating career-ending hazard. Thanks for joining me for this explainer, and please stay safe out there.